static electricity. Okay, let's use this to solve the problem. A single loop of wire of radius 5 centimeter carries a current of 3.2 ampere. What is the magnitude of the magnetic field on the axis of the loop, one at its center? Well, that is the earlier case that we had considered. 2.5 centimeter from the center. We got to use the exact formula there. 75 centimeter from the center. Well, 75 centimeter, x equal to 75 centimeter is very large when compared to the radius 5 centimeter. We will use the approximate formula there. So all we need to do is use the appropriate formula for each of those. Field at the center of the loop is mu 0 I over 2r, and we have all those values, substitute them, and that gives you the field at the center of the loop. Second case, the field at a point 1 centimeter from the center. Well, that's a small error that I made. I have used 2.5 centimeter here, and I used 1 centimeter here. So what I suggest you do is correct that to 1 centimeter. So, what is the field at 1 centimeter from the center? We use the exact formula, where we know the radius, x equal to 1 centimeter, which is 0.01 meter, and substitute all the given values, knowing that mu 0 is 4 pi times 10 to the negative 7 Tesla meter per ampere, and that gives you the magnetic field at that point, 4.65 times 10 to the negative 5 Tesla. And finally, the field at 75 centimeter, we use the approximate formula, mu 0 I r squared over 2x cubed, and that gives you 3.49 times 10 to the negative 9 Tesla. So this kind of problems, very simple and straightforward. We will now discuss a law called Ampere's rule. Ampere's rule. Now, Ampere's rule is similar to Gauss's law in static electricity. You remember the net flux crossing an area is 4 pi k times q inside. Now, let's develop the Ampere's rule using the results we already know. The equation for the magnetic field produced by a current in a long straight wire, you recall that, is B equal to mu 0 I over 2 pi r, where r is the distance of the point where the field is discussed. Now, Ampere's law gives us a general relation between current in a wire of any shape and the magnetic field it produces. Now, I'm going to read the law and then interpret it. Ampere's law states that for any closed loop path, now here I have a diagram, here is a conductor that is carrying a current I, and what all we need to do is take any closed loop path around that conductor. Now that's what the law is talking about. Ampere's law states that for any closed loop path, the sum of the length elements times the magnetic field in the direction of the length element. Now remember, if you take a closed path around this conductor that carries a current, there will be a magnetic field anywhere along that length. Now, in order to take Ampere's law, the field must be in a direction parallel to the length element we take. For example, here I have taken a length element delta L, and we need to therefore take the component of B along that delta L. That means you take delta L multiplied by B that is parallel to that delta L. And you do that for each element and add them all together. That's what this means. Summation of B parallel times delta L. the sum of the length elements times the magnetic field in the direction of the length element is equal to the permeability times the electric current enclosed in the loop. So summation B parallel times delta L is mu 0 I. If you cannot see this on the screen, the right side of the equation is mu 0 I, permeability times the electric current enclosed in the loop. If this is the loop, the electric current enclosed in the loop is that I. Now this law is analogous to Gauss's law we talked about. Now Ampere's law can be expressed as a path integral. What's the meaning of a path integral? Integrate along the path. Now summation B parallel times delta L is actually integrate along the path of B parallel dl. So that will be integrate B dl, same as this. The summation is replaced by integral over the path of B dl equal to mu 0 I, and that is the statement of Ampere's rule. Let's do a small problem. Two long wires are oriented so that they are perpendicular to each other. One carries a current of 20 ampere in the positive z direction, and the other carries a current of 5 ampere in the positive x direction. At their closest, they are 20 centimeters apart. Calculate the magnitude of the magnetic field at B, magnetic field B at a point midway between them. Now, here, this is the situation. This is a wire that comes out of the board. We would say into the board is negative Z, out of the board is positive Z. And there is another wire 20 centimeters below it, like this, which is carrying a current in the x direction. Well, let's draw that diagram. Now, this is the situation. This is the conductor that carries a current of 20 ampere in the positive z direction. It comes out of the board. And this is the conductor that is carrying a current of 5 ampere in the positive x direction. We need to find the magnetic field at P midway between them. Alright, let's use the equations that we developed so far to do this. So the top wire carries a current of 20 ampere out of the paper or out of the board in the positive z direction, and the bottom wire carries a current of 5 ampere in the positive x direction. The field P due to the current in the top wire, can you use the right hand rule and tell me what will be the direction of the field at this P due to the current in here? You see, the current is coming out towards you. So I'm going to stand here. I'm going to keep my thumb pointing at you. Can you see that? And I'm holding the wire like this. That means the field will be like this, going in the positive x direction. So the field due to this wire will be in the positive x direction. How about the field due to the current in this wire? The current is that way, so I'm going to keep my thumb pointing that way, and I'm going to wrap my finger. Look at the way it's coming out. It's going to come out of the board. It's going to come in the positive z direction. So the field at P due to the current in the top wire is in the positive x direction, and the field at P due to the current in the bottom wire is in the positive z direction. That means you need to find the resultant of those two. And the field at P due to the current in the top wire, use the equation mu 0 I over 2 pi r, where I is 10 centimeter and the current is 20 ampere, and that is 4 times 10 to the negative 5 Tesla in the positive x direction. Similarly, field due to this wire will be the same equation where I equal to 20 amp, where I equal to 5 ampere. Is that right? You need to correct that. The bottom wire carries a current of 5 ampere and the distance R is 0.1 meter. That change, so the field at P due to the bottom wire is 1 times 10 to the negative 5, a quarter of that. And therefore, what is the resultant field at P due to both? This is the field due to the top wire. This is the field due to the bottom wire. So the resultant will be, therefore, square root of 4 times 10 to the 5 squared plus 1 times 10 to the negative 5 squared. That is 4.12 times 10 to the negative 5 Tesla. Alright, let's now look at what is called a solenoid. What is a solenoid? Now what I have here is a solenoid. It is made up of a